Hi. Up to this point, we've mostly been focusing on local maxes and mins. Today, we're going to learn about absolute maxes and mins and how to find them. So we're using derivatives this time to find the absolute maxes and mins. Now, we introduced them before so that you could determine the difference between a local or relative max and min and an absolute, but we stepped aside and now we're going to actually be finding them. So remember that relative or local max or min is just the highest or lowest in a little interval. It does not have to be the highest or lowest on the entire graph, and we are talking about y values when we say maxes and mins. An absolute max is absolutely the highest on the entire graph or on the graph, the portion of the graph, the interval of the graph that you are given. And an absolute min is absolutely the lowest on the whole graph. And so what you can see from this picture is that an absolute max or min could occur where we already have been looking at these local or relative maxes or mins. So for instance, this is the absolute min for this function on this interval, and it happens to also be the bottom of the valley, and so the lowest thing in a little interval and is a local or relative min. The other place that we can find absolute maxes and mins is on the endpoints. So if you have a closed interval, then you would have a filled-in endpoint on the end here. Now, this function probably would have kept going up forever, in which case we couldn't say it had an absolute max, because if it keeps rising forever and it heads to infinity, then I can't name a finite number that's the highest point. But by chopping it off here on a closed interval, now it does have a highest point. So that is the other place that we can find these absolute maxes and mins. And that's really going to be it. This section is one of the most straightforward sections, and I hope that you will not make it harder than it is and really enjoy this question when you get to it on the test. So here's our definitions, and we already talked about those, that they're highest and lowest on the interval. Now, we also have a theorem that says if we have a closed interval, so it has to be a closed interval, and it has to be a continuous function, then you will always have both an absolute max and an absolute min. So we're guaranteed to have one. Now, if this is not a closed interval, if this is an open interval, we may not have both, and we'll look at that as well. But for the closed interval case, that is the most classic one of these problems for absolute maxes and mins. You can absolutely expect to see one on the test, and it's really quite straightforward. So if we're going to have an absolute max or an absolute min, it's going to occur at either a critical value or an endpoint. So what we're going to do is take the derivative. That's been the first step of just about every problem in this unit. Find critical values, and then we do need to make sure that those critical values are in the given interval. And I don't think I have one of those in these notes, but do watch out for it on the homework, that if your interval is 1 to 5 and one of your critical values is 7, you don't want to consider that going forward the rest of these steps, because it's not in the interval you're looking at. So you make sure you list the endpoints of the given interval and any critical values that are in that interval. And then we are not having to do first derivative tables, none of that. We are simply saying these are the only places an absolute max or min could occur. So let's check their y values, because we're literally seeing how high or low it is. Is it the highest or is it the lowest? And so we're going to plug those endpoints and critical values that are on the given interval into the original function and find the highest and lowest. And that is it. That's the whole thing. Okay, so let's look at one. So you would be given a function and a closed interval. Remember, this is interval notation, meaning you're starting and including an x value of -6 and going into 2 and including 2. And so we are going to find the critical values. So first derivative. If there was division, if there was a place it does not exist, we would think about that. But we're going to take the derivative, which is 3x squared minus 12, set it equal to 0. We can factor a 3 out, then it's a difference of squares, and we get 3 times x plus 2 times x minus 2. Now do remember that you only get answers from factors that have x's in them. So don't tell me x is 3 and don't tell me x is 0, right? I only get the -2 and the 2. So those are my critical values. They are both on my interval. One happens to also be an endpoint, but they are on the given interval. If one of them wasn't, I would not include it going further. So then I list all the critical values that are on the given interval and any endpoints. And I tend to list them in order. It doesn't matter though. So my first endpoint is -6, then -2 was in between my interval, and then 2 happened to be both a critical value and an endpoint. Then, lastly, I'm going to plug those 3 possible places where I could have an absolute max or an absolute min into the original function, because that's how I get y values, and literally see which is the highest and which is the lowest. So I do make sure I'm using my original function, not my derivative, and plug in -6, I get -144. I plug in -2, so this is just the things from my list, my critical values on the interval and endpoints. And I get 16, plug in 2, and I get -16. And then I label which is the highest and which is the lowest. So -144 is absolutely, right, the smallest number out of all of these. And so that's our absolute min. Some questions will ask you to state it as an ordered pair, and it would be -6, -144. Some questions will have fill in the blanks to make sure you really understand that a max or a min is a y value and that the x is when or where it occurs. So it might say absolute min of, and you would type -144 that occurs when or where or at x equals -6. So you might see that as well. And then the highest number we got when we plugged in was 16. That's my absolute max. I could list it as an ordered pair, -2, 16. Or I could say I have an absolute max of 16 because a max or a min is a y value, and that it happens when or at x equals -2. That is it. That's the whole problem. They really are that easy if you make them. So there's no tables here. There's no first derivative tests. There's none of that. The only possible places we could have them is here, so we just see the highest and lowest. Now we are going to see one other kind of problem, but you can definitely expect one of these, the very straightforward closed interval problem. So what if we don't have a closed interval? And now we're going to learn this, although most of it's going to actually be reserved for the word problems in our next section on optimization. But this is kind of when we would learn it. So what if we don't have a closed interval? Okay, this is another, and I don't care about the names of them because it depends what book you're using as to which one's called 1 or 2, but this actually ends up being basically the second derivative test, and that's how I will refer to it. So if you have a function and maybe it's not a closed interval, it's an open interval, that's okay, but you find critical values and there is only one, exactly one, critical value that's on that given interval, then what that's saying is that if you zoom in on that, it may not really be a parabola. It may not actually be like a quadratic function, but if you zoom in on that spot, it would kind of look like a parabola, right? That's where we would have a single critical value, and so it's either a max or a min. And to verify, instead of doing a whole table, because these are actually absolute and not relative and all of that, if I just check the concavity there, I will know which one. So I have this value C, which is a critical value, which automatically means it's a possible max or a min. If I check its concavity, if I see what the second derivative is at that x value, and the second derivative is negative, okay, so if my second derivative is negative at this place that's a possible max or a min, then at that location my function is concave down. So what does it look like? It looks like a max, and that's all there is to it. Okay, so if I have this one critical value, so it's my only possible answer, so I hope it's going to give me a max or a min, and I check its concavity. So I check the concavity there by plugging that x value, that critical value, into the second derivative, and I find that the sign of the second derivative is positive, then that means my original function is concave up. So if I have this thing that's a max or a min, and it has a concave up shape there, it must be a min, okay? So we've already looked at these when we did second derivative curve sketching stuff. And so when your second derivative is negative, your original function is concave down, and if I was going to draw a max or a min, I'd have to be drawing it on the top there, and it would make a max. When your second derivative is positive, your original function is concave up, and so if I was drawing a max or a min, it'd be there at the bottom, and it'd be a min. So sometimes I have students that try to like memorize this because it seems backwards to them that like a negative is a maximum. But you don't need to do any of that. You already know those two statements back from the second section we covered. to be able to talk about intervals of concavity. So you already know that when the second derivative is negative, you have concave down. Now just tell me what that looks like. It looks like a max. Or when you're concave up, it looks like a min. Okay? So if you were given a problem like this, you have to be given a function, but you were not given an interval. So if you're not given an interval, you don't just make one up. If no interval is given, it means we're using the domain of the function. Now for this function, it's a polynomial, and that's negative infinity to infinity. So we use the whole domain. Notice that is not a closed interval. So when it's not a closed interval, I can't compare the y value of that I get when I plug a critical value into the y value that I get when I plug in endpoints. And if I don't have anything to compare to, then that way is not going to work. So that's why I cannot use our other method when I have an open interval like negative infinity to infinity. So if I get that when I plug in my critical value, I get 1,000,000, just because that's a high sounding number, if I can't compare it to the endpoint values, I don't know that that's necessarily a max. What if the ends go up and actually if we did chop it off, you know, that's a min and the function goes even higher than 1,000,000. Okay? So when it's an open interval, we're going to use this other method. It does not make sense to just find the y value because you have nothing to compare it to see if it's higher or lower than other things. All right? So open interval, negative infinity to infinity. As long as we get exactly one critical value, then we can use this second derivative test. And you're going to, okay? Or at least one critical value that actually makes sense in that domain. So first step of almost every problem we do, find the derivative, right? First derivative, if there were any does not exist kind, I would think about it, but there aren't. So I set it equal to 0. 4 minus 2x equals 0. Add the 2x or add the 4, whichever way you want to go, and divide, and you get 2. So I only ended up with one single critical value. So that means I have this possible max or a min. I don't think, you know, I just need to see which one it is. Does it look like this, in which case it's a max? Does it look like this, in which case it's a min? Okay? So I take the second derivative because concavity will tell me that. So here's my first derivative. The second derivative would be 0 minus 2, or just negative 2. I plug in this critical value, this possible max or min, in to see what the concavity is there. Well, if I plug in my critical value of 2, because this happens to be a constant function, then I'm still going to get negative 2. So that is going to happen quite a bit where our second derivative is a constant, but not every time. So if this still involved a variable, then I would actually have to compute what happens when I replace my variable with the critical value that I'm plugging in. But if it is a constant, then no matter what I plug into it, I will always get that constant. So I don't actually care about the value, but it's negative 2. What I care about is that it is negative. So I have this thing that's a possible max or a min, and when I check the second derivative is negative there. That means my original function is concave down there. Again, that goes back to our second unit. We've known that, a second section, since then. So I have this thing that's a possible max or a min. It looks like that. Which one is it? It's a max. And so now I have found that this critical value is going to result in a maximum value, and then I go find it. So the one nice thing about the closed interval is that while you're figuring out which one is which in terms of max and min, then you're also getting the y value at the same time. Here, we're kind of back to some of our previous work where, okay, I've identified that this is an absolute max, and then to find the y value, I, of course, need to use the original function. So I'm going to go back to the original function, evaluate f of the critical value that I've now verified gives me an absolute max, and I get 4. So I have an absolute max at the ordered pair 2, 4, or it might be stated that there's an absolute max of 4 at x equals 2. Okay? So if we have an open interval, then there's not going to be a trick question. So you're going to end up with just a single critical value, and you are using the second derivative concavity to tell you which one it ends up being. Then, as always, we go back to the original function to find the y to say the actual value of it. So I just want to show you this is the exact same function, but now it's a closed interval, and I'm doing that to compare what can happen when you have an open interval versus a closed interval. So with that open interval, it ended up that it looks like this. It goes down forever, so I can't name an absolute min, because if you tell me it's a negative 1,000,000, I'll say it's negative 1,000,001, and it keeps going. There's no finite number that it stops at. So we only had an absolute max. We did not also have an absolute min. Now, when I have a closed interval, that extreme value theorem tells me I will have both. So I will definitely have both an absolute max and an absolute min. Now, because we've already done this problem, we know what the absolute max is going to be, because if that was the absolute max for negative infinity to infinity, then as long as that x value is on my interval I'm talking about, it'll still be my absolute max. But I want to do it from scratch so that you can see another example of one of these closed interval problems and know how to do it, but also to compare what happens when you have an open versus a closed interval. So we've got a closed interval. We will find critical values. First step, as always. So to find critical values, I need to take the derivative. I would get 4 minus 2x. Think about the does not exist kind, but there aren't any. And so I have 0 equals 4 minus 2x. So I'm solving, dividing by 2, and I get that x equals 2. We're not surprised because we've already done this, right? So that is my critical value. Then I would list, because this is a closed interval, I would list all the endpoints and critical values that are on that interval. So I have an endpoint of 1 that came from right here, okay? Then 2, my critical value, is in that interval, and then I close off my interval at 4. So I've listed them 1, 2, and 4, and I like to kind of label so you know where those came from. Then these are the only possible places that I can have a max or min, and I will have both absolute max and min because it's a closed interval. So I'm simply going to plug those into the original function, no tables, none of that, and simply see the highest and lowest. So I will do f of 1, f of 2, f of 4, where all of these are f, the original function, 4x minus x squared. So f of 1 gives me 3, f of 2, when I work it out, gives me 4, f of 4 gives me 0. And so then I look for the highest and lowest. So I plug the critical values that are on the interval and endpoints into the original function to find the highest and lowest. So let's look at that. So looks like my highest value I got was a positive 4. So that'll be my absolute max of 4 at x equals 2, or as an ordered pair, 2, 4. And then my absolute min looks like it is 0. So because I ended this, then I have it cut off, and it doesn't keep going down forever. And where it's cut off ends up being my lowest point. So as an ordered pair, that's 4, 0. Or if I was asked to fill in the blanks, it would be that there's an absolute minimum of 0 that happens at x equals 4. So to compare, here we had the absolute max of 2, 4. We had something like this going on, and we had arrows where it kept going down forever. And so we couldn't name an absolute minimum, and we're not guaranteed one if we're on an open interval like we were with this negative infinity to infinity. But then in this problem, we cut it off, and we had some endpoints, and so now there is an actual lowest point. So of course the highest point, because it was on the interval that I'm looking at, has not changed because it was the highest for the entire negative infinity to infinity. But now I can actually name a lowest point because I've chopped it off with a closed interval and I have a filled in circle there. Okay, so what we are going to do in general is all these started with taking the derivative. All these started with finding the critical value. So that's a great first step. If you don't know what to do, at least do that because I can give you points for that. Then I have to consider, is the interval open or closed? So if the interval is closed, we're going to plug those critical values that we found and that are on the interval and the endpoints of the interval into the original function and look for highest and lowest. Done. If the interval is open, so that could be negative infinity to infinity, could be 0 with an open parentheses to infinity, then I cannot do that because there's nothing to compare to. I have no endpoints to compare to. But what I can do is say, well, I only have one. It either looks like this or like this, right? It looks like a hill or a valley. And then I use concavity to tell me which one. So that's when we use that second derivative test. So I have one more example that we'll look at, both to give us practice with that second derivative test, because you do see this as an open interval. I'm actually more interested in this problem because I worry about the algebra of it, which of course is review, but I want to make sure you've seen it, and then you'll see another one of these when we get into the word problems where the algebra is kind of similar, so I hope that it'll help you with homework and with that going forward. So here's my function. I need to find the critical values, which means I need to take the derivative, but to do that I first need to rewrite it with x to the negative 1, or I guess you could use the quotient rule, but it's kind of extra work. So now I will take the derivative. Derivative of 4x is 4. Here I bring down my power, subtract 1 from my power, and get minus 64x to the negative 2. And then I want to rewrite it so that I know what that actually looks like. And the reason I wanted to do that is because don't forget about those equal 0 kind of critical values, right? I'm sorry, the does not exist kind of critical values. So notice that if x was 0, we would have division by 0, and so this derivative would not exist. However, it's not in the domain of the original function, and nor is it in the interval we were given. So it might look like you have more than one critical value, which would be bad, because our method only works if we have exactly one critical value in the interval. But we don't, because I can't call that a critical value because it's not in the domain of the function. It's not in the interval I was given. So x equals 0 is not a critical value. So then I look for the equal 0 kind. So I set this equal to 0. Now I want to see, use that form so I can really see what it looks like. So I want to solve for x, but when I say solve for x, I'm trying to get x by itself in the top, not in the bottom. And so that's going to be my motivation for why I do the steps that I do. I need to end up with x in the top. So first I'm going to add the 64 over x squared over to the left to isolate the term with x in it. Then I need to multiply both sides by x squared so that x lives in the top. Now remember, we're not going to have any issues here because we already said x can't be 0. So now I get cancellation on the left, and I have 4x squared. It lives in the top now, which is good. That's what we mean when we say get x by itself, on one side. We're not there yet, but at least it's in the top. So now we have 64 equals 4x squared. And we'll divide both sides by 4 to isolate the x squared, and then undo a square with a square root. You have to remember that whenever you introduce a square root into a problem, if you take the square root of both sides to undo a square, you always get plus or minus. So formally, and your work really should show that you got plus or minus 4, because that is correct mathematics. However, I can then throw out negative 4 because it wasn't in my interval, right? So it's not in 0 to infinity, so I'll throw it out. So your work really should have it, because that is what you get when you solve this equation we're working on. But x equals negative 4 is not in the given interval, and so there's only one critical value that is in our interval. And that's good, because when we have an open interval, we can only have one critical value, and then we just check concavity to see which one it is, an absolute max or an absolute min. So here's my derivative. Here's the critical value. I'm ready to do that second derivative test. Notice that I wrote the power rule version because that makes it ready for me to take the second derivative. I now take the second derivative. The derivative of 4 is 0. And here, when I bring that power down, it'll be positive 128. And now subtract 1 from the power, x to the negative 3. So the second derivative is 128 over x cubed. I have this x equals 4, which is a critical value. It's a possible max or a min. If I plug it in, I will use concavity to see which one it is. So when I plug 4 in, I don't know what that is. You're welcome to use your calculator to find out what it is. I do want to see your second derivative. I do want to see that you're plugging 4 in. But a positive 128 over a positive 4 cubed is positive, and that's all I need to know. So we do get a positive. So I have this possible max or a min, but the second derivative is positive. When the second derivative is positive, right, remember our smiley face, the function is concave up. And so if I had this thing that was a max or a min, it must be a min that I'm talking about. So I'm going to have an absolute min. I'm not going to have an absolute max because this was an open interval, so I'm not guaranteed both. And then I can actually find that y value. So remember, we always go back to the original function to find a y value, the actual minimum value, because a max or a min talks about how high or low you are, which is a y value. And so my original function was 4x plus 64 over x. And so that's written on a previous page. So this is with plugging 4 into it. So we have 16 plus 16, we get 32. So we have an absolute minimum at 432 as an ordered pair, or we have an absolute minimum of 32 that happens at 4. And so now we have seen multiple examples of both a closed interval problem and an open interval problem. As I mentioned, when we talk about the test, we are going to get to continue to use this open interval absolute max min second derivative test method in our word problem section that we're going to cover next. So that's kind of already covered there, but now is the time to introduce it. So if I can only ask you one question On absolute maxes and mins in its own right, it is probably going to be a nice closed interval question like our first problem and our third problem, I believe, okay, where you plug in the critical values that are on your interval and the endpoints into the original function and literally find highest and lowest. And then, as I said, this is going to be a nice quick and easy way versus drawing a bunch of tables and such to help us verify something in our word problem. So we will use this, but it'll kind of be built into other problems. All right, so that's it. That'll be our last section. We'll be putting all this together to identify absolute maxes and mins in true application problems like business applications and other optimization problems.